So here I am on a late September day, a blustery day, with Keyron Hickman-Lewis, a microbial paleontologist at Birkbeck College at the University of London, we've been talking about some fascinating research on the search for early life here on Earth. And Keyron, can you tell us, one of the first questions I asked you just now in the interview is, you do a lot of research in looking for ancient microfossils embedded in sedimentary rocks, but also mudstones here on Earth. How difficult is it to find bona fide evidence, direct evidence for microfossils here on Earth, much less Mars or anywhere else?
No, indeed. So it can be very challenging. Many of the oldest traces of life have extremely simple, extremely simple morphologies. These are the kinds of morphologies that can be easily reproduced by other natural processes. So we really have to find microfossils that are extremely well contextualized, extremely well understood in terms of their geological and their environmental context. We need microfossils that have been preserved over billions of years, so we need favorable preservational conditions, and we also need a multitude of analyses that will tell us what is the composition of these organisms, how did they live, what were their metabolisms. So it can be extremely difficult and increasingly difficult as you go further and further back in time, when
what you term deep time,
deep time, indeed, 2 or 3 or more billion years ago, in the very early period of Earth history. There are very few of these rocks remaining, and the ones we have are often quite badly altered.
And I just held in my hand a kind of a slide, a tranche of a stromalite, I believe,
Right.
which offers, it's not a microfossil, but you told me it's the oldest known indirect evidence pointing to life on Earth. Is that correct?
So the oldest known direct evidence.
Evidence of life on
direct
Earth.
evidence. It's a 3.48 billion year old stromatolite from the Dresser Formation in
the
Western
Pilbara,
Australia, in the Pilbara, and it's a kind of microbial construct. It isn't a microfossil. Itself. It's the kind of structure a community of organisms might build. Very much the same as people build houses and skyscrapers. So too do microbes build a construct that we can recognize in the rock record, and so stromatolites are sequentially layered biosedimentary structures, and they have a record up to about 3.5 billion years.
So if you told me if it were a microfossil itself, that would be direct evidence. Is that correct, or am
That's
I
correct.
misconstruing?
So microfossils and the kinds of morphological structures that they build, I would class as direct evidence of past biosphere, of past life
here
on
Earth.
Yes, indeed.
And you also told me that you think that there is, you wouldn't say direct evidence, but you did say indirect evidence somewhere here on Earth of life that's maybe as old as 4 billion years old.
I think this is correct. Certainly we have some very compelling indirect chemical evidence of life up to 3.8, possibly 3.9 billion years old. I think it's a very reasonable that up to this point we have potential evidence of a biosphere. It isn't direct evidence. It isn't a microfossil. It isn't a trace. It isn't a trace fossil, but it's a trace of the impact of the biosphere on
on the
our planet.
On
yes,
the planet.
On the planet. Yes.
So, and all of this, we talk a lot about sample return missions from Mars and whether Mars ever had microbial life. And I think it's a lot of people, with few exceptions, most people think Mars probably had some form of microbial life in the past. But the last question I asked you in our interview just now was, what are we missing in the search for life on Earth? And the interesting thing is that came out during our discussion was that the oldest microfossils that we have found on Earth are really almost from the four corners of Earth at high latitudes. But that's not necessarily where these microbiologies originated.
No,
we
that's
know
right.
we find evidence for past life in microfossils in the Pilbara region of Western Australia, in South Africa, in Western Greenland, and also
Canada, India,
also India,
yes.
Which is not
yes.
as
not
well
as
known.
Well known.
We were talking about that. So, but just because they are kind of at the four corners of the Earth, so to speak, that's not where they necessarily originated. And until we perfect our paleomagnetic detective techniques, maybe with new technologies, we won't be able to determine where on Earth these microbes originated, correct?
No, this is unfortunately correct. We have them in these locations now because that is where they have ended up after billions of years of history, and they are fortuitously preserved at the Earth's surface, and we can analyze them in these regions. But that's probably not where they started.
So one final question, and that is, from a global sense, what do you think we're missing in the search for the onset of life on Earth?
Indeed, I think really what we're missing in terms of the origin and the earliest evolution of life is the direct evidence of the environment, of the geological contexts in which this happened. And I hope in the future that this is some information that can possibly be filled following Mars sample return. We know that the surface of Mars is extremely old. It's much older on average than the surface of the Earth, and it's conceivable that there are horizons on Mars that date from the time of the origin of life on Earth. So I think we're missing these kinds of samples, and I hope in the future there'll be a kind of change of paradigm. At the moment, we use what we know of our understanding of Earth as a tool to understand Mars. I hope in the future we can use some of the information we get from Mars as a tool for understanding Earth in deep time, which is a record we simply don't have here.
And by geological context, you mean exactly the geology that underpins, as you put it, the life that started here. So in other words, if it's in a volcanic splash zone, which would mean,
or if it's at a hot spring or
hydrothermal
if it's a submarine hydrothermal vent. I think this is the kind of contextual information we are really missing. And as much as we can try to recreate certain conditions under laboratory conditions, having natural evidence of these processes and samples that bear the results of these of these processes would really be an unparalleled opportunity for.
So
our field.
Keyron Hickman-Lewis, thank you so much for your time today here at Birkbeck College, University of London, on a very cool, I think it's unusually cool.
Unusually cool September.
Unusually
Yes.
cool September, but there you go. Thank you so much for your time today.
Thank you very much, Bruce.